Good morning. I'm Scott Arnold, Senior Manager of Publications and Standards for AMCA International. Welcome to Fan Fundamentals, Understanding Curves and Performance Characteristics. In preparing this session, AMCA met the standards and requirements of Registered Continuing Education Program, or RCEP. RCEP's involvement should not be deemed or construed to be an approval or endorsement of the content of this session. The information contained in this session is provided by AMCA as an educational service. In making this educational activity available, AMCA is not endorsing, sponsoring, or recommending a particular company, product, or application. Finally, this session is protected by U.S. and international copyright laws. Reproduction, display, distribution, and use of the material without written permission from AMCA International is prohibited. And with that, let's meet our presenter. James Mathis joined the New York Blower Company in 2016, shortly after graduating from the University of Illinois at Chicago with a bachelor's degree in marketing. He started in the technical support group, gaining broad knowledge of the company's products and working on special pricing and custom catalog quotes. In 2019, he moved into project management, overseeing complex projects often heavily specified to applications such as API, sanitary, and wastewater treatment. He moved into his current role of OEM sales manager in 2023. James?
Thank you, Scott. A quick story. About 2 years ago, I was at a customer's facility for training some service techs on troubleshooting, among other vendors, and I'm watching the dust collector expert go up, and he's halfway through his presentation, and he opens a slide with a picture of a fan on it, and he says, "Fans, the bane of my existence." Now, growing up in the fan industry for the last 10 years, I, of course, think fans are extremely cool. I imagine most of you agree. But the reality is the people that use fans just need them to work. They don't want to think about it. They don't want to deal with it. It's an ancillary piece of equipment. And to get a fan to really work and run healthy in the field, it starts with a good selection and a base understanding of the fundamentals of what kind of fan makes the best sense for a particular application. Now, a few learning objectives before we get into the presentation. By the end of this presentation, our hope is that you'll be able to apply the fan laws that we're going to talk about today to calculate changes in performance, to describe the different flow control methods, compare them and understand how they're used, to understand the basic principles of a fan selection, to compare different fan types, wheel types, and know why you might use one of them over another, and to explain non-standard air and know how it impacts a fan selection. I'm going to start with a couple key terms common in the air movement industry, starting with CFM. Cubic feet per minute is a measure of airflow. SP stands for static pressure, often quantified in inches of water gauge, and it's really a measure of resistance to airflow in a system. RPM is revolutions per minute, typically talking about the speed of a fan's wheel, if not the driver that's running the wheel. You've got BHP, brake horsepower, is a measure of horsepower consumption for the fan to run at a given operating point. So we're going to start with a few fan laws that look at how a change in a fan's speed affects a change in a fan's flow, pressure, and horsepower consumption, starting with the relationship between speed and flow. And to conceptualize this diagram does a good job. If you think of the blades on a wheel as a series of equally sized shovels, each moving an equal-sized amount of air or matter as they rotate, then it would follow that if you increase the frequency with which each equal-sized blade moves an equal-sized amount of matter, that the speed change and the flow change would have a one-to-one relationship, which is what the first fan law says. That the change in flow, or CFM new over CFM old, is equal to the change in speed, or RPM new over RPM old. Now, we'll run through a operating example. You've got a fan in the field on the left. It's running at 10,000 cubic feet per minute. It's generating 10 inches of static pressure. It's running at 1,000 RPM. And to do all that work, it's consuming 100 brake horsepower. We're going to double that speed from 1,000 to 2,000 RPM. We know from the first fan law that the flow will also double from 10,000 to 20,000 CFM. Going to static pressure, similar setup, but you might see it's much more sensitive to a change in speed because it varies as a function of the change in speed squared. So we started with 10 inches of static pressure, so x over 10. is equal to our speed change ratio, that's 2 because we doubled it, and 2 squared is 4. So x over 10 equals 4, solves for 40 inches. You've quadrupled the amount of pressure by doubling the amount of speed. And then brake horsepower, the most sensitive to a change in speed. It varies as a function of the change in speed cubed. So we started with 100 brake horsepower, so we have x over 100 equals 2 cubed. So x over 100 equals 8. Solves for 800 brake horsepower. Now a lesson here is that if you need to change something in the field, maybe a fan and a system aren't interacting as expected, you're getting a little low on flow or pressure, a common way to react to that in the field is to speed up the fan. And it's not going to be perfect. You have some kind of estimate or calculation on a system drop that the fan has to match to balance that pressure and move the airflow through. And you might need to account for some amount of headroom in the motor size so that you have a little bit of flexibility with the speed. Now, when you approach a fan selection, there's a lot of things to consider. I'm not going to read all of this to you, but you've got the aerodynamics. If you have a fan, you need airflow. And consequently, you need pressure. It's going to take a certain amount of consumption. And then you have what's going through the air and what's it made of and what decisions does that drive about materials of construction or the right geometry in the product line. You've got the physical considerations. How big of a footprint can you handle? How high are your ceilings and your doors? What are your power restrictions or your noise requirements on site? We'll walk you through that kind of process as you select a fan. Starting with the capacities. If you need a fan, you need airflow. So you've got ACFM, maybe it's CFM or SCFM. And really, pressure is often, in this industry especially, just kind of something you need to be able to move that flow through the system. So fans are pressure-sensitive devices. If you look at a curve, you've got the fan curve and the system curve. The fan can only move the prescribed amount of airflow if it's truly intersecting with the amount of pressure that the fan is seeing in the system in terms of pressure drop. So you got pressure, which is often static pressure, complete total pressure, might be velocity pressure, but in the end, it's just what you need to deliver the flow through the system. Then you have density, the weight of the air, the mass per cubic foot. So we start by defining standard air, which is the density of air, its standard conditions, and standard conditions are 0 feet above sea level, 70 degrees Fahrenheit. And at that density, you got 0.075 pounds per cubic foot. And things change that, temperature, elevation, rarefication. So let's start with temperature, specifically cold temperature, something that's relevant if you're dealing with cold start in the field. So you've got a fan, and maybe it runs at 200 degrees Fahrenheit, but it starts by drawing ambient air in Minnesota, and it's 0 degrees Fahrenheit. That air weighs a lot more at 0 degrees than 200 degrees, and you have to find some way to not overload the motor while you bring your process up to temperature. So one way to do that would be with speed control. You slowly ramp up the speed of the fan as your process comes up to temp, or you use an inlet damper to slowly open up that damper, allow more airflow to load the wheel and therefore the motor to make sure you're not overloading the motor. That's the idea of a cold start. Then you have hot temperature. If you're dealing with about 600 degrees Fahrenheit, the density is half that of standard air. You want to select it for the worst case scenario. So look at the cold temperature, look at the hot temperature, and understand what speed you need, what horsepower you need, and size it for that. And then you have altitude. At 18,000 feet, density is half that of standard air. Now, I don't know of a lot of fans installed on a mountaintop, but you don't need to correct it for everything. At about 1,000 feet above sea level, that's when it's going to start moving the needle. You don't need to really think about it too much if you're dealing with 200 or 300 feet. And then rarefication, something that won't come into play much in this industry. If you have a good amount of suction pressure, then you have to start accounting for the rarefication that thins the air as it enters the wheel. You want to start thinking about that around negative 15 inches. Then you have airstream makeup. You know about your aerodynamics, but what's in that air? Is it hot? Is it moist? Is it corrosive? Is it flammable or explosive? And all that starts to get you thinking about what material of construction makes the most sense and what fan makes the most sense, what blade geometry can handle what's going through the airstream. So let's start with flammable or explosive materials going through the airstream or gas. AMCA has developed 3 tiers of spark-resistant construction, meaning certain components in the airstream are constructed of material that's 5% or less of iron, so it's non-ferrous. Now, AMCA A would be the most comprehensive, where the entire airstream is constructed of non-ferrous material, often aluminum. AMCA B is the picture that we're looking at now, where only the wheel is constructed of non-ferrous material, and then buffers adjacent to the wheel. And AMCA C is buffer-type construction, where you only have non-sparking buffers welded to the inlet and the drive side of the fan. So if the ferrous wheel moves, it's designed to hit non-sparking buffers before it hits the ferrous housing. So you know your aerodynamic requirements, you know what's going through the fan, and now you have to think about what fan makes the most sense. So if you're dealing with small amounts of dust and smoke, typical for this industry, you're dealing with a backward inclined fan or maybe an axial fan. If you start getting into light dust, fume, or moisture loading, there are some kinds of backward inclined fans that might be able to do it, some that won't, or a radial centrifugal fan. If you're dealing with high particulate loading, which is a material handling fan, then the radial bladed fan family is going to be the only thing that can really handle that. You also have noise to think about. Noise is a nuisance. There are requirements about the maximum amount of noise that's allowed from a certain amount of feet from the source of the noise, considering the reflectivity. Is it in a field, which is going to be pretty quiet? Is it surrounded by steel equipment that's going to create a lot of reverberance and magnify that noise? And it varies with things like the geometry of the wheel or how much flow or pressure and efficiency. The more efficient a fan is, the quieter it's going to run. You also have the physical constraints to think about. How much of a footprint do you have? How sophisticated of a machine can you deal with? Or do you really just need a small footprint and the least maintenance possible? So let's start with direct drive fans, where you've got the fan, wheel, and the motor running at the same speed, connected somehow. Now, there are pros and cons to both arrangements. We'll start with an arrangement 8, where you have the motor shaft connected to a coupling. The coupling other half connects to a fan shaft that's supported by bearings, and then the end of the fan shaft connects to the fan's wheel. So big footprint. You've got bearings and a shaft to maintain, and including to the wheel and the motor. It's a big footprint, but it's flexible. If you have high temperatures or a wet airstream or corrosives, the motor can't really be exposed to any of that. So there are pros and cons to both. You can compare that to an arrangement 4 fan. Much simpler, smaller footprint. The motor connects directly to the fan's wheel, but it can't handle any of those things. It's got to be a very clean, low temperature, dry airstream. You also have belt drives as an option, where you have shibs or pulleys that vary the speed between the motor shaft and the fan. Starting with arrangement 1 fans. It's kind of like the arrangement 8. It's a big footprint. You have your motor isolated from the airstream, which gives you the same flexibility of an arrangement 8. It's mounted on a separate frame typically, which is often known as a unitary base. But now you've got a base that you have to buy and belts that you have to tension with the slide base. Compare that to the arrangement 9, much smaller footprint, where the motor is tucked on the side of the pedestal. You still have the belts, you have a smaller footprint, but you also have a motor that's right next to the housing. So if it's a hot airstream, it's going to radiate to that motor, and you've got a limitation. Then you have inlet considerations to think about. And fans, the inlet and the outlet condition are both critical. That's a system effect topic that we had someone cover earlier this week. But if you have to be biased towards the inlet or the inlet is going to be more critical. And so we have a couple different examples here. And when you look at the data of fans' performance in the fan curve or a catalog, it's based on perfect testing in a lab. Open inlet, long ducted outlet that's long enough to straighten the air, or the reverse. In the field, that's not as feasible. You've got to have elbows, filters, dampers that create pressure drop that you have to account for. So looking at the left inlet, you've got an elbow that's going to create a pressure drop. You also have a good amount of straight run of ductwork to help straighten that out. It also takes up a lot of space to do it that way. In the middle, you see where they didn't have as much space, and they dropped it right into the inlet and did a 90-degree turn. Now, there's a good way to do it, and there are bad ways to do it. Ideally, you want to do a 90-degree turn into the inlet with a manufacturer-designed inlet box by the same people that made the fan. Because most of them have tested their fans with their inlet boxes. They know what the associated pressure drop is. You can often go to their fan selection software, add the inlet box, click to hold the pressure, and watch the speed increase to overcome that loss. And you have flow control to think about. There are various reasons to do it. Maybe you have various needs throughout a production cycle. Or maybe you're planning to do one thing with the fan today and another thing in 10 years when you have a plant expansion. There are different ways to do it, and they affect a fan curve or a system curve differently. You have fan dampers. You have speed control through variable frequency drives. And for certain specialty axial fans, you have variable pitch blades. So let's start with dampers. You have the outlet damper that bolts to the outlet. You have a variable inlet vane damper, and you have an inlet box damper. The inlet box damper and the variable inlet vane damper do the exact same thing. We'll talk about that in a minute. Starting with outlet dampers, you have a couple different kinds. You have a parallel blade damper where the blades open parallel to one another. You have an opposed blade where they open opposite. The parallel blade damper is going to give you bigger swings and flow control. The opposed blade damper is going to be finer tuned, but more straight and laminar airflow. When you close off the dampers of an outlet damper, the blades on an outlet damper, you're kind of simulating a system that has more resistance to the airflow. You're restricting airflow, you're lowering it, and you're adding pressure. So you're not changing the fan. It's already left the fan. Now you're changing the system part of it. So as you change the blades on an outlet damper, you create new system curves, not new fan curves. You can have bolt-on external dampers, or you can have internal dampers that are built into the casing, much lighter duty, more cost-effective. Now the inlet damper, the variable inlet vane damper, works completely differently. As you close off the blades, it creates a pre-spin of the air as it enters the wheel. It spins it in the same direction it's about to spin once the wheel gets a hold of it. What that does is it diminishes all aspects of performance. You get less flow, less pressure, less horsepower consumption, kind of like slowing down a fan, but I'll show you how the curves differ. You have variable pitch blades. Certain kinds of axial fans have the blades that are able to spin. On the most simple level, you have a manual variable pitch blade where you take the hub cover off, and you have a threaded rod and a nut that you can change the blades uniformly with. Some people can also do it in flight or in operation. We have automatic pitch change through either pneumatics or hydraulics, where you can often change it while the fan's running. And then speed control, which is becoming more common as they become a little more cost-effective and user-friendly. It's a very efficient way to change this fan speed. And as you change a fan speed, you create a new curve every time. Increase the speed and the curve goes up, decrease it and it goes down. So we'll look at these top three curves today to understand what that looks like on a curve. Starting with the left, we have an outlet damper. Remember, I said with an outlet damper, you're not really changing the fan's behavior, you're changing the system. So as you close off the outlet damper, you create new system curves riding one single fan curve. In the middle, you have the opposite, the inlet damper. Whether it's a variable inlet vane damper or an inlet box damper, they do the same thing. They create a pre-spin, and now they are changing the fan's behavior before it enters the fan. So as you close off the variable inlet vane damper blades, you create new fan curves riding one system curve. And then you have speed control, kind of like the inlet damper curve. It creates a similar shape, but it doesn't umbrella at the middle, because now you're creating a new speed, a brand new curve. You can see the geometry. It's the same fan. All right, so you know your aerodynamics, you know what's going through and what materials of construction make the most sense. Now it's time to consider what fan makes the most sense for that job. So we've got two big families we're going to cover today. We've got centrifugal fans and axial fans. We'll start with probably the most common fan in this industry, the backward inclined fan, which is the most efficient of the centrifugal fans. They get their name because of the backward inclined orientation of the blades. I'll show you that in a minute. They're very clean air fans. Depending on the wheel, it may or may not be able to handle some light amount of dust or moisture. It really comes down to the blade. And these are used to create moderate to very high amounts of airflow at low to moderate amounts of pressure. A couple nuances about the backward inclined curve. Starting with this green line, that's the fan curve. It plots the combination of pressure and flow a fan can hit at a given speed. You've got this area to the left of what's called peak pressure. That peak pressure, and to the left of it, is an area of instability. If you selected a fan here or had it inadvertently running there in the field, it would be very turbulent. The flow would be inconsistent and bouncing around, and with that, you'd see vibration. Sometimes it could be violent enough to fail a fan pretty quickly. Sometimes it could be pretty unnoticeable, but if you took a flow reading, it wouldn't be the same at all. It'd be bouncing. You also have what's called a non-overloading horsepower characteristic on the blue curve. It peaks and drops off as you get closer to what we call wide open flow, which is maximum airflow and minimum pressure. Now that's counterintuitive because as you get to maximum flow, that's also max weight. If you multiply the density by the flow, you've got mass flow, or the pounds you're moving per minute. So at that bottom right corner of the curve, you're pushing the heaviest shopping cart, and yet it's consuming less power than it was when you were pushing a lighter shopping cart. So this gives you an idea of the backward inclined nature of these blades. In the orientation we're looking at, the wheels would be rotating clockwise. So those wheels sit in a backward incline. One of the reasons they're not very good at handling material or moisture is because the backward incline tends to build material unevenly on the back side of the blade, which creates imbalance. We've got a single thickness blade on the left, what's called an airfoil blade on the right. We'll start with the single thickness. Simple rectangular blades, solid. And for that reason, they can handle some amount of light, dust, or moisture, but not much more than that. They get to see about 80% efficiency. You can compare that to the airfoil wheel. It has a similar shape to an airplane wing, and it's hollow on the inside, so it can't handle any moisture, because that could create condensation and build on the inside of the hollow pocket, or it could create abrasion, or material in the airstream could eat right through it. But with that sacrifice of material handling and a more aerodynamic design, you get up to 90% efficiency with this. As we go through these, you're going to notice maybe that there's an inverse relationship between the efficiency of a fan and its ability to handle material. It's not an accident. It's just the things that you do to make a fan very efficient take away from its ability to be rugged. This is a picture of an airfoil wheel that was misapplied in the material handling airstream. You can see the wear pattern and where it eventually ate right through that blade. It's going to create serious imbalance issues. Now, when you look into the outlet of a backward inclined fan, the wheel usually only takes up about half of that width. The other half is a critical piece to any backward inclined, or really backward inclined fan's performance. It's the inlet cone. And the inlet cone is critical to that fan keeping the pressure and flow that it's designed for. You notice that top right corner, we've got a formed sheet that's called a cutoff sheet, because as that air moves through the housing, it's got mass, and it might have the tendency to recirculate through a fan. You need the cutoff sheet to kick it out and move down the process. So the inlet cone, its location is critical. It's got to be centered radially in the inlet shroud's lip, and the wheel is typically welded. It's not going to be perfect, but the idea is you have to have it as centered as possible, and the depth, the insertion depth, matters a lot. So this picture, you see the inlet cone tapers smoothly in to the lip on the inlet shroud. Our service manager once told me that if you feel, obviously when the fan is off, along the inlet cone, you should feel a very smooth transition from the cone to that lip on the inside of the shroud. If you have it lined up like that, you're utilizing the full width of the blade to move the flow. You also have these common two adverse conditions. On the left, you have an inlet cone that's overshooting that shroud. You can see it's not utilizing the full width of the blade. You're going to have a loss of pressure and flow. On the right, the inlet cone doesn't insert enough. You have a gap between the cone and the lip of the inlet shroud. tends to recirculate and not really utilize the blade width at all. Again, loss of pressure and loss of flow. Now there are some alternative configurations for a backward inclined fan. The wheel we were looking at was a single width, single inlet. This is a double width, double inlet. You basically take two wheels, you put them together on a common center plate, and that doubles the amount of airflow while keeping the amount of pressure constant. That's because the width of a centrifugal wheel is what moves flow, and the diameter is what creates pressure. You notice that the blades are offset instead of in line. That's because as those blades pass the cutoff sheet that I showed you, it creates what's called a blade pass frequency. If you've ever stood in front of a subway and the cars pass and the gap between each car pass, it gives that vroom, vroom, vroom. It's the same thing as a blade pass frequency. That minimizes it by offsetting the blades. You also have what's called a center hung configuration here, where the shaft is on both sides. It means your bearings are on both sides in the inlet of the fan or in the airstream. Now bearings are also very sensitive. You can't have moisture or material in that kind of an application. What you could do is add inlet boxes on the inlets and extend the shaft and the bearings to sit outside of the airstream, and then you have some more flexibility. A plug fan is another common variation for a backward inclined wheel. We have a wheel that can handle the extreme temperatures of typically a freezer or an oven, but you need to separate that and insulate it from the more sensitive drive components, belts, bearings, motor. You have a panel that you can make thicker as needed for 4, 8 inches, insulated with mineral wool or not, depending on the temperature. Then last, you've got the tubular centrifugal fan, a chaotic combination of centrifugal air movement forced down a tube axially. You see the inlet cone, because it's needed on every backward inclined wheel. And you use this if you need the combination of the flow and pressure that you get from a backward inclined fan, but also the convenient ductwork, sandwich installation or rooftop installation. And because of that chaotic combination of centrifugal airflow being forced down a tube, you've got these straightening vanes that are critical to straighten that air out, help it be nice and laminar. At the same time, it costs 5% of efficiency. You've got an obstruction in the airstream. Similar concept to if you have a poor inlet condition on a fan, you might have different kind of straighteners that could help straighten that air as it enters the inlet and improve the performance, but it's also a pressure loss. Example of a backward inclined installation. This is pulling fumes off of a plant. And this is a good picture because it shows a lot of good accessories. First, you've got the inlet duct dropping down through a round to rectangular transition into an inlet box to make the best possible 90-degree turn into the inlet. Discharges through an outlet damper into a rectangular to circular transition and into an elbow with an outlet silencer on the end. So a lot of accessories being deployed here. Radio-bladed fans, I'm not going to spend too much time on. They're not very relevant in this industry. But radio-bladed fans are kind of the opposite of backward inclined. They create moderate to high amounts of pressure at lower amounts of airflow. They are material handling fans, and some more than other. And again, because of that material handling build that goes into these, they're not as efficient. The picture here is a very straightforward wheel in the radio-bladed family. It's called a paddle wheel. Excellent at handling material. Not very efficient. Compare that to the dust handling wheel. This is about as efficient as a radio-bladed wheel gets at only 65 to 70%. But again, the things you've done to make it efficient, you've curved the blades, you've added a sponge shroud to the inlet. That's creating a lot of hang-up points for materials, stranded material, string, to caught between those blades and the inlet shroud. Just another example of that inverse relationship. Then you've got kind of a hybrid fan called a radial tip fan. It's got the ability to fill in some of those intermediate points of the curve that might be too low pressure for a radial bladed fan and too high flow, but also you get the efficiency of a backward inclined fan. It uses an inlet cone because it does have a backward inclined orientation to the blade. You could see that in this picture. But if you look at the 1 o'clock position of this picture, you see where that backward inclined shape deviates to a radial tip. That's how it fills out the higher flow, high pressure, very efficient points that a lot of other fans can't. And then you have pressure blowers, kind of a unique radial bladed fan. It's not at all used for handling material. It's used to generate tremendous amounts of pressures at very low flow. Common in pneumatic conveying, we use them a lot in boilers, and also in combustion air. You might tell just by looking at it, this is not a material handling wheel. We've got sponge shrouds, riveted construction. The width alone wouldn't be very useful in moving material. There are steel open inlet designs, but they're really for moving pressure. You've got the forward curve centrifugal fan. These are good at moving a relatively large amount of airflow at a relatively slow speed, thanks to a lot of blades that are forward curve. They cup the air and move it, which is a good design for moving a good amount of air at a slow speed. And that becomes useful because these are often used in hot applications. Blow dryers, car dryers, most of your furnaces at home use a forward curved wheel. Aside from HVAC, these are often used in makeup air kits. We'll get that to in a minute. But again, riveted construction, delicate, thin gauge blades, not a material handling wheel. Often called the squirrel cage wheel, not sure why. And then you've got the forward curve fan curve. It has kind of a combination of the backward incline and radial bladed fan curve attributes. You've got the dip on the fan curve and the peak that you want to stay at least 5% to the right of to prevent stall. And now you have an overloading horsepower characteristic. The more weight the fan moves, the more power it consumes. That makes sense to me. So makeup air unit, a very common use for forward curve wheels. If you have a building that's exhausting air, it needs to replace that air so it's not under vacuum. If you've ever been to a restaurant, you're trying to open the door and it's pulling against you, it's under some sort of vacuum. An example would be a restaurant that's exhausting it on a grill with a hood. You've got to replace that air, and that's what these are used for. Now, axial fans branch off completely from the centrifugal design. They move air in a straight line. They're used for creating very high amounts of flow at very low amounts of pressure. Commonly used for general dilution, ventilation, and also replacement air. The axial fan curve also has a peak you want to stay to the right of. And it also has a non-overloading horsepower characteristic like the backward inclined fans. Now, vane axial fans actually use airfoil blades. Same design as a backward inclined fan, but they're oriented to move air in a straight line. Often welded to the hub, and the hub is typically larger than 50% of the diameter of the blades. And the ratio between the hub diameter and the blade diameter has to do with how much flow versus pressure it's biased toward. The larger the hub, and therefore the shorter the blades, the higher the pressure and the lower the flow. If you have a very small hub and longer blades, you've got less pressure and more flow. And sort of like the inlet cone that's so critical to a backward inclined fan's performance, you have tip clearance on an axial fan that you need to create its performance. It doesn't have a lot of pressure to lose, so you need to have tight clearances, usually 1/8 of an inch, and any more than that, you start to lose pressure and flow. Often what people will do is these blades are typically cast. They'll oversize them, and after they have the housing welded, which isn't going to be perfect, then they machine them down to size. A duct fan is more of a light-duty, cost-effective version. Similar use, higher flow, lower pressure. You no longer have that cast airfoil blade. It's a simpler form design, less blades, and the hub is typically less than 50% of the overall blade diameter. A lot of paint booth exhaust, general dilution, and ventilation. And then the propeller fan. No duct, just a simple prop that blows a lot of air and moves very little pressure. You see these often installed in agricultural buildings on the side for ventilation or drying. Now, a common vane axial application would be combustion air. In combustion air, They don't need volume, they need mass. They need pounds and pounds of air for the amount of combustion they need to off-gas. In this case, you have an axial fan. They need a lot of air because they need a lot of weight. They don't care much about pressure because this is it's a pretty straightforward design. It's a stack. There's not a lot of resistance to it, so this makes it a good fan for the job. Another example would be grain drying. You've got a stack of fans that are blowing a lot of air through heaters, and then into these baffles that have grain falling through them. I'm going to leave you with a few resources that you have access to. First one is our fan selection software. It's called Fantasize. This is free for you. You don't even need to make an account. And you start by selecting the fans that make sense for what you're honing in on. And the less fans you select, the faster it will run. Then it will take you to a page where you enter in your inputs. It has to know pressure and flow and density. There's a calculator that will help you come up with your density if you're not sure. Then you can give it as much or little as you know, the size, wheel type, materials of construction. Then it will take you to a list of fans that meet your criteria. You could filter from here on size, wheel type, horsepower consumption, lowest speed, cost per year of operation. And lastly, it'll take you to a page where you can fine-tune your selection. You could change width or diameter of the wheel to change the position on the curve. You can add an inlet box or a damper and see how the pressure drops and the speed increases to hold the pressure that's needed. You can see the fan horsepower consumption or the total horsepower consumption with belt losses and VFD turndowns. Then you could also print any data sheets. You can print curves, data sheets. You can do drawings through a program that gives you drop downs so you can select everything for the fan and get a model, STP, DWG. Then a few AMCA resources that we've found helpful in the past. Starting with AMCA 201, discusses effects of inlet and outlet conditions. That's getting into system effects. There's also a good YouTube series, if you look it up, for NYB that our VP of Engineering did on the topic. AMCA 202 is a troubleshooting manual, in-situ fans. And AMCA 203 gives you the methods for taking field performance measurements on a fan if you need to know how it's performing in the fan or in the field compared to whatever curve or data sheet you have. What questions do you have? Yes. A plug fan? So he's asking which type of fans would be used for a plug fan?
Yes, and which type of this fan accepts is it classified under any of these fans presented in your lectures?
Yeah, so the plug fan would use a backward inclined wheel. You could typically use a single thickness or an airfoil wheel. You could use backward curve. Those are the three typical backward inclined wheels. But other people will get a little more creative depending on what's in the airstream or how much flow versus pressure. We've seen people use axial wheels in plug fans. We've seen them use radial bladed wheels, but typically it's going to be a backward inclined wheel. Anybody else? Yes?
I'm not familiar with the term rarefication. Can you explain that?
Sure. So he's asking about rarefication. That's really thinning of air. And it really, for the fan context, it comes into play with a lot of inlet pressure. If you have a lot of suction pressure, which isn't very common in this industry, it starts to thin the air. Rarefication is thinning the air. And in this case, it lowers the density of the air. And therefore, it changes the speed that you have to run at to hit an amount of pressure or flow and the amount of horsepower it's going to consume. Yes? Yep. He's asking about the different types of flow, ACFM, SCFM. So ACFM is actual CFM. That's what's most common. There's also standard CFM, standard cubic feet per minute, and that looks at mass flow. So ACFM is a measure of volume, the volume of air per cubic foot. And then you have the mass flow, SCFM, which is your density, say 0.075 times your flow, say 20,000. I think you've got about 1,200 pounds per minute that you're moving. And some people don't care about volume, they care about mass flow, which is SCFM. And then you've also got pressure on the topic. You have static pressure and velocity pressure. It's the pressure around and still, and the pressure as it moves, that's velocity pressure. You add velocity pressure and static pressure together, and you have total pressure. Yes?
For ACFM and SCFM, I've heard different definitions as well. So SCFM is at sea level 25 degrees centigrade.
Right.
Density. Actual is if you're up in 10 or mile high, density is different and all of that. That's what actual CFM is.
Right. Actual CFM and standard CFM have to do with where the density is being taken from. Standard CFM is always standard conditions, 0 feet above sea level, 70 degrees Fahrenheit. Yes. Yes.
For fans in non-standard housing configurations, is state-of-the-art to run CFD modeling to actually figure out flow, or are there kind of simpler ways or rules of thumb that you use to figure that out?
Yeah. The quickest way, if you have the information, and actually, the fan selection software will help you with it when you get to this page, but let's say you have a plenum fan, which is very common in this industry. It'll ask you for the distance from the wheel to the wall. It needs to know the size of the plenum that it's in. And if it's not that certain what size it's going to be, and it doesn't take into account the other dimensions aside from the width, CFD modeling would be very helpful. I think it's always a little bit unknown, and the deal is that there's very little pressure, there's very little resistance at plenum. So you get a fan that has a couple inches typically. It's a pretty low pressure application, and you have a good chance of getting your flow. But I think CFD is really the way to guarantee it, if not just understanding I forget the name of the factor, but the distance from the wall of the plenum to the center of the wheel. Anyone else? Yes.
A lot of the systems I deal with are much smaller than what you're kind of presenting on, but I was curious between, like, for a fan that needs different speeds, is there a longevity performance difference between like a dual winding AC versus an EC, and what might be the factors for selecting each?
You talking an EC motor versus an AC motor? I couldn't speak to it. Truthfully, we're a little odd at this conference. We're more of an industrial manufacturer, so we're only just getting into EC motors. We've got a lot to learn about them. Well, I'll leave you with this final thought. I've thrown a lot at you today, high level, broad, and I know you've been to other presentations as well, and the idea is not to remember all this. You've got access to it. You'll get the presentations. You've got access to our website, nyb.com. It's not a plug, it's educational. They have engineering letters, our fan selection software, you'll find through it. And once you know where it is, you don't have to remember it. Thanks a lot, everybody.